So let me just mention there are special events happening. Job fair starting in a few minutes on Zoom. So if you want to go to that, that's probably very much worth your while. You can just watch the recording of this stuff later. There's a event with Pacific Hackers and YSys. I think they're going to have lockpicking as well as social engineering here, and they're going to have food. So you might want to register in advance if you want to come physically and get a chance to the food and the lockpicking. If you connect in online, you'll be able to watch the talk at least, but you won't be able to do these hands-on activities. And the Hacking Club will be back in a couple of Saturdays, so that you can do that physically or come in by Zoom. Those are all good things to do, and they're all worth extra credit. All right, so let's talk about OllyDebug. We've already started using it. OllyDebug has been around for a long time. The source code was purchased and rebranded as Immunity Debugger, which is essentially the same. All right, so if you want to debug malware, you can load the malware directly in OllyDebug. You can also attach it to a running process. So you open an exe, it'll load in the debugger and stop at the entry point. This is how most all debuggers I know work, because they figure you want to see the code and add more breakpoints or examine the registers and things like that. You can attach to a running process, but then it will be somewhere in the middle of its running. So you normally don't want to do that, but you might have to under certain circumstances. You can reload the current executable with Control F2, and you can use F2 to set a breakpoint. These shortcuts are handy. You can do it all from the menu too. By the way, reloading the executable is very common. You're playing with it, doing things, you get lost, and you just want to reload and get a fresh start. I do that a lot. So we've talked about the interface. In the top left, you have the disassembler. You can see the raw hex value, and you can see the disassembled code. On the right, you see your registers, like ESP and EBP are the main ones we're paying attention to. On the left, bottom left, you have a memory dump of any region of memory you want, with addresses, hex, and ASCII. And on the right, you have the stack. And the stack mostly has return pointers. So it can return from things, but it also has local variables and so on. You can see the stack there. So, all right, so you can modify data. You can go to the disassembler window on the left and press spacebar, and then you can edit this code by typing in new assembly language code. We'll do that in the demo later. You can modify the registers or the stack. And you can edit any memory region with memory edit. So that's the point. You can modify data in any of these. All right. One thing I'll mention, though, is if you change memory anywhere here and you want to save the modified executable, save it right away. What I found the hard way is if you change things down here and you change things up here and save it, you won't get both changes. It only saves the changes in the current segment of code, like the text segment, the data segment, and so on. So the best policy is if you change anything, save the file immediately. And then the next change, save it again. When I didn't know that, I drove myself crazy trying to modify code and being very frustrated at the fact that the modifications didn't seem to always stay correctly. Let me check for comments in the Twitch. All right, nothing new there. All right, so the memory map, you can just view memory and you'll see the memory and you'll see it's owned by various processes. So here, for example, is the user libraries. Here's the shell libraries. The libraries are sitting in memory and they are executables. But the main thing you care about usually is the primary executable you're debugging. Here's one of the malware samples, and you see it's got a PE header at an address ending in even thousands. This is where if you don't relocate them with address space layout randomization, all Windows executables want to load at 400,000 in hex, which is not really 400,000. It's a bigger number. It's base 16, but it looks like 400,000. And then you've got the text section here, the RData, and the data section. As you see, we've talked about this before, the code, imports, and data. You'll see where it is here. You can see the use of memory. Rebasing is when a module does not load at its preferred base address. Portable executables want to load at 400,000. If they can't load at 400,000, they will relocate somewhere else. And if they support address space layout randomization, then they'll often be relocated, of course, just for security. DILs are also more commonly relocated because a single application can import many DILs. Windows DILs, when Microsoft writes them, they assign different base addresses, so they're more often able to just load at their base address just to make it a little more efficient. Relocating takes a little time and makes them a little less efficient. All right, so here you got absolute versus relative addresses. The first three instructions will work fine, even if it's relocated, because you have calculated addresses, EBP plus var8, that will move relative to the base pointer. So if the stack has been relocated somewhere else in memory, it'll find it. The same thing here. But this third address, this one, oh, this is a named location, 40120, so that might be all right. But this one has an explicit word, explicit value, a direct address in here. And therefore, if you relocate this code somewhere else in memory, it won't be able to jump to this address and it'll break. So when you do that, you will have to change this address. And that's what goes in the relocation section. You'll find it in the PE header, an extra section like text, R data, and data. There's a relocation section, and that lists all the instructions that have to be changed when code is relocated, which is the extra work that you would avoid if you don't have to rebase them. So that's a thing to know. All right. And so here's an example of code with text, data, resource, and a relocation section. All right. This is something called device metadata parsers.dil. All right. So that's DIL rebasing. You can remove the relocation section, and then it can't be relocated, and it must load at its base address. And as I showed you last time, you can use set DIL characteristics to remove the flag from any executable to stop it from relocating, which often helps you analyze it. All right. So here's DIL rebasing. Here, two DILs try to load at the same memory, which looks like 1 million or 10 million, 100 million. I think it's 100 million, a lot of zeros. So DIL A got to load there. DIL B could not load there, so it rebased to somewhere else. So the program will have, the operating system will have had to use this relocation section and modify the text to go there. So it had to do some extra work to load the second DIL that couldn't load at its preferred address. All right, IDA Pro, which we'll get to later, IDA Pro doesn't know about rebasing. So if you compare the addresses in OllyDbg and IDA Pro, you might get different results. That can be very confusing because IDA Pro is not really running it, so it doesn't go through rebasing. It just shows you things in their preferred location. So that might not be where they really are in memory. And that's another thing that confused me until I got it straight. Right, you can view threads if you want to. See, the threads are little parts of a process that can proceed independently. You don't normally debug things at this level, but you can. And each thread has its own stack, so you can, it can get pretty complicated. Heaps get really complicated in Windows too, but none of the stuff we're going to do is going to go into that deep an area. So ASLR, people are beginning to think that ASLR is not really too important. It's not as good as it should be. Arguing about it, but people are still using it. So it's really out there. Some people say it's not as good of a defense as it should be, but it did end a whole generation of malware. ASLR and DEP, Data Execution and Prevention, stopped all the malware up there like Windows XP. There was a whole bunch of malware using these simple buffer overflow exploits, and none of them would work anymore with these new security measures. There are ways around them, but people had to rewrite better malware, and that's all you ever do. You make a defense, and the bad guys have to work harder. So you can run code in OllyDbg. F9 will just start running and run until it hits some kind of stopping point, like a breakpoint or a pop-up box to ask the user for input. You can pause a running program, although this is usually not much use because it runs so fast. Breakpoints are better. You can run to a selection. You can execute till return, execute till user code. But the normal things I use are F7, F8, and F9. F9 to just run. F8 to run. Take one step at the current depth, and if the next command is a call, do everything in the call until you have a return, so you come back to the same level. F8 commonly, and F7 if you want to step into the call, because usually the call is still code written by the developer you're interested in, and you want to go in there. You don't want to F7 all the time, because pretty soon you'll be in the Windows DILs and the Windows kernel, and you probably don't want to mix your time in there trying to debug Windows. All the stuff I'm doing, I'm trying to debug, I'm trying to understand the malware. I'm not trying to find bugs in Windows itself, which is a much bigger, more complicated task. So I use F8 to stay out of the windows and step at a higher level most of the time. So you could run and click pause where you want to be, but of course, how would you know where to stop? I mean, I guess if you're playing like a game, you might see the bad guys running around the screen and know where you want to pause. But unless there's some kind of obvious graphic display like that, it's going to be hard to stop at the right place. So setting a breakpoint is usually better. You can run to selection. That's just a way to click a point to select it and go to that point without bothering to set a breakpoint. You can execute until the return of the current function. That might be useful if you're in a subroutine and you say, okay, I want to get out of this subroutine back to whatever called it. That's one way to get to do it. And execute till user code, that's a good idea too. Get you out of all the libraries. Run until you stop being in libraries. If you do end up having dug yourself into some Microsoft DIL code and you don't want to be there, this would be a way to just run until you get back to stuff that is not a library. And they say the main thing you use is F7, F8, and F9. F9 to run with no restriction, F8 to step over, and F7 to step into. All right, so let's try a Kahoot. I think it's 9A, isn't it? Let's see, this is chapter 9. Yeah, good. So here's 9A. All right. All right. Let me take a look and see. Well, I think here we can see it. I'm going to maybe make it this way a little bit there. So hopefully people can see the number you need to see to join the Kahoot. Well, we may not have very many competitors tonight. All right, we will carry on. All right, so which objects are never rebased? Yep, if it doesn't have a relocation section, the DIL files are often rebased. But if you have a portable executable file without a relocation section, it can't be rebased. It has to load at its preferred address. And I guess if that address is unavailable, it will just give you an error message and fail to load. All right. All right, which key press modifies assembly code? It's the spacebar. Control F2 reloads the program. Spacebar modifies the assembly code you've selected. Which key press steps over? F8. That's the right answer. Good. All right, which key press runs until user code? Oh my, I think I do this one by process of elimination. Yep. Alt F9, because I know F7 and F8 and F9 are simpler activities. All right, so it's going to be all three of you, all the competitors. Although you have to tell me who they are, recall us a lot of points. I know who Hacker Kitty is. why we say it. All right. Anyway, let's go back. See. All right. And what's here? Min will use Zoom at 7:30. All right. All right. So let's go back to here. All right. So breakpoints. We talked about these before. You got software, hardware, conditional, and breakpoints on memory. The most common type is F2. You get that with the ones that turn red. Those are software execution breakpoints. It replaces a byte with CC is what it does. And so you got that software breakpoints. You can have conditional breakpoints that test some condition to decide whether to resume automatically. You can do the hardware breakpoints, which are in the processor. There's only 4 of them, but that's one way to make a breakpoint without modifying any of the text section. And you can have memory breakpoints on access when it reads, writes, or executes memory or writes. So there's various ways to do it. All right. If you save close all debug, it saves your breakpoints. If you open the same file again, the breakpoints are still available. It must be saving some kind of Ollie debug file to go with the program. Sort of interesting. Might be interesting to go find that file and see how it works, but I never have looked. So software breakpoints are very handy for all sorts of things. One of the many things you might do is put a breakpoint so that when it decodes something, it'll you can stop it after it decodes it and before it erases it. Put a breakpoint at the end of the decoder, then it becomes readable on the stack. That's the sort of thing. This is very common. Conditional breakpoints are things. The Poison Ivy backdoor was a Windows XP rootkit, and it allocated memory to house the shellcode. So if you put a breakpoint on virtual alloc, you'll have every memory allocation, but most of those are not interesting. So you'd want to only have a breakpoint if the memory being allocated is sizable, and you could do that. You could put a standard breakpoint. It'll keep on breaking at that point. And then you can make a conditional breakpoint that says only break if the stack pointer has made more than 100 bytes of space here. So you're only if I'm allocating a large amount of space will you put a breakpoint there. That's one example where you might want a conditional breakpoint. The hardware breakpoint doesn't slow down execution or alter any data, but there's only 4 available in the processor. All right, and you can have memory breakpoints, which Ollie debug simulates. It does this, I think, by using CC, and then I think it's basically conditional breakpoints where it goes into the Python-based debugger and decides whether to resume. But anyway, you can break on anytime the location is read or written or other such things. You can only have one memory breakpoint at a time, and say it's got considerable overhead, and it's not reliable. So it's possibly useful, but might lead to trouble. All right. And so if you want to know when a DIL is used, for example, you could open the DIL's text section, put a breakpoint at access, and then you'll know whenever it tries to read, write, or execute that area of the DIL. So that would be a way to find out when a DIL is used. All right. Now let's try another Kahoot. 9B. Like we're going to have only 3 people, maybe the same 3 people. If one person changed their name, that's fine. All right. All right, so what's the most common breakpoint? software breakpoint, software execution breakpoint is the default F2 one. That's all I've ever used. It's good enough for most purposes. All right, what kind of breakpoint lets you only have one of them? The breakpoint on memory is the one. It works by changing permissions of a memory segment, and you can only do it to one location at a time. What key press sets a breakpoint? F2. All right, which breakpoint has 4 but no more instances? Hardware breakpoint, that's right. There are only 4 of them. Okay. So, loading your DILs. You can't load a DIL directly, so OllyDebug uses a dummy executable to load them, and then breaks at DIL main, which is the code that executes to prepare a DIL for use when a DIL is first loaded. And you can play it to run DIL main and prepare it for use. So I'm not going to do this live, I'm just going to talk about it. You can, if you try to call the exports to enter this program, you load ws232.dil, which is a networking DIL. Implementing WinSockets, which are the standard Berkeley standard sockets that made the internet. You can reload the DIL and run once to run DIL main. Now you can call the DIL exports, and you'll see the functions that are available here. And one function we have here is N2HL. There's a list of other functions available someplace, but I think just a drop-down box gives them. And this function is incredibly simple. This just reorders bytes. You see an address here, 7F001. This is 127.001. And you can reorder it into the other order, putting the 1 at the front. That's all this subroutine does. And so you can run it directly in here. You can run it and see the output. It's kind of clumsy, but it is possible to run one function in a DIL while you're there. So it just converts a 32-bit number from network to host byte order. All right. They're not really worth demonstrating, but you do have the ability to do that if you want to debug functions at that level. You can also do tracing. Tracing records all the execution information as it goes, so you can actually use like an undo in Microsoft Word to go back. So a standard backtrace, you can just use the minus key in the keyboard, and it'll move back to the previous instructions, but you won't see the previous register values. So it's not really like undo in Microsoft Word. It just shows you where you came from. Plus and minus will move back. But if you want to, you can do a call stack trace. This will show the sequence of calls to reach your current location. This is quite commonly done to show you how deep the call stack is. And so here, for example, there's a simple guessing game where you ask it for launch codes, and if you get it wrong, it insults you. And so this is the entire function of this. We'll modify it later. We'll play with this. It's a real simple program. And you can step into puts, which is the Windows API call that prints on the screen. And now, if you view the call stack, it will show you I started, here's the module entry point, here's the string printing launch codes, and here's the kernel stack below it. So it shows the call stack that led to my current position. If you step in again, then you'll see a new function appearing at the top. So anyway, you can see the layer of functions you've been through here. I expected to see the main program there, but anyway, we'll play with this later on, I think. Anyway, you can watch the call stack and see how many layers you are deep. All right, here's a deeper call stack. I went to one of these Lab 09s and I just went deep into the function and broke it, and you can see you're called from this. So this is called from this is called from that, and you're many, many layers deep in many different functions. That's what kind of situation you actually have in a running program of any complexity. And then run trace is this thing that really lets you do the whole undo like Microsoft Word. You highlight a region of code, you do run trace, and then after you execute it, you can go forward and backward with everything changing. It's expensive, but you can do it. I mean, it costs a lot of processing time and memory, that sort of thing. You can add it to selection, and then you can run back and forth through the code. All right. You can trace into and trace over. If you don't set breakpoints, it'll try to trace the entire program, which might take a long time and a lot of memory. All right. And you can trace until a condition hits, sort of thing we talked about before. You can use this in complicated situations. I've never used these. Might be possible in some of the tough cases. I found it possible to get by just using single step and step over to get through things. And then there's exception handling, which is going to come up a lot in later projects. When an exception occurs, the program stops and it returns. You can then decide what to do. You can step into the exception, step over the exception, or run the program again and see if the program is going to handle the exception. Often you just ignore exceptions in malware analysis because if the malware has a bug and triggers an exception, we don't really care. We're not trying to debug them, to remove bugs from malware. But some of them use the exceptions to run code. Then it would matter. And then patching something. You can binary edit things. Right-click binary edit to change code. You can fill with NOPs, fill with zeros. You can type in assembly language code if you use assemble with the space bar. You can modify code. That'll modify what's in RAM, so you can run it in its modified form, and you can save it on the disk and have a modified executable. Let me go back and check for comments in the Twitch. Can anyone else join Steve Nelson's job fair? Well, I hope you can. I haven't checked. All right. Anyway. All right, so you can fill a region with 0. You can fill it with NOPs. This is what you might do to skip code, and we'll do that in a demo later. And you can save the patched code. Like I say, right-click, copy to executable, all modifications. I've warned you, this all modifications isn't a lie. It doesn't do all modifications. It only does all modifications in the current code segment, which would be text or data or something. So the best thing is save after each change, or you might find that some of your changes didn't get saved. So you can analyze shellcode. You can make a region of memory and show a hex dump, and then you can change it in memory map to make it executable. So there's one possible way to do it. I've never done this. It's easier in my experience to just make a C program that runs your shellcode to test it, but you can just test it directly in Ollie Debug. All right. And there's a log that showed all the steps you took to reach where you are, which might be useful. And there's something called watches where you can watch an expression. I haven't used it here, but I have used it in WinDebug, a similar thing. You can do things like watch calls and see the arguments of the calls. So if you're running something like Notepad, you could print in WinDebug, you can get Notepad to print the name of every file it creates. Now you can't do that in Ollie Debug with any current version of Notepad because now it's 64-bit, I think. Maybe it's 32-bit. I haven't checked Notepad. Anyway, you can label things, of course. If you want to analyze a big block of code, you can add labels like comments to help you understand the code. Something you do more often in Ghidra or IDA Pro, but you can do it in Ollie Debug also. And there are plugins that add extra features. And the only one we're using here is the Ollie dump we talked about to dump the debugged process to a PE file. That's useful for manually unpacking code. You can also have one that tries to hide the Ollie debug from debugger detection. So hopefully will fool malware into running even if the malware tries to avoid being debugged, and other things you can add. All right, and you can add scripts to it. Immunity Debug employs Python script and has an easy-to-use API, and you can write easy scripts. And we are going to use some scripts when we get to use Immunity later to develop some Windows exploits. So that's 9C. I think that's on the other class. 127, we're going to do that. We're going to use some Immunity scripts, Mona in particular. Anyway, let's take a look at the last Kahoot, 9C. And let me see. I think I have to sort. See if I can get 9C to show up. Well, 9A, 9B, and another 9B, but no 9C. That's rude. Well, I guess I won't run it. Maybe I lost it or it never existed. At some time I thought there was a 9C, but there isn't, so I'm not going to run it tonight. Maybe it's in the wrong folder or something. All right, so that's it for the lecture. Let me stop.